Alrighty, grade 12s. Let's look at vertical projectile motion. Alright, this is a nice topic in physics. Alright, quite a nice topic, and believe it or not, probably arguably, alright, if something's arguably, then that means it's usually debated or argued over, of course. It's arguably the most failed question in a matric exam. Arguably, okay? Because a matric exam structure, here in the Western Cape, which all of you are from, of course, and if you've looked at a past matric paper already, if you haven't, I am worried, and I would encourage you to look at a past paper as soon as possible so you can get the structure down, because the structure doesn't change. Your section B starts off with a grade 11 Newton's laws question, moves into a vertical projectile motion question, right, which is the second question of question B, question 3, and then moves into your momentum and impulse question, which is question 4, and then question 5 moves into your work energy theorem question, which is going to come up very shortly after vertical projectile motion, and then you end up into question 6. But question 6 usually isn't a mechanics question. Right? Usually that's your Doppler effect question. Okay, but sometimes they might switch the work energy and power over 2 questions. Okay, usually they might do that. But usually, coming back to vertical projectile motion, that is question 3. Always. Right? Standard. Okay. So, we've all done mechanics from grade 10 up until now, and we all are actually familiar with equations of motion. Now, up until grade 11, which was last year, boys and girls, equations of motion have dealt with horizontal motion, delta x. Okay, delta x being displacement on a horizontal surface, a flat surface. Okay. I'm standing right now on, which is my bedroom floor. It is a horizontal surface, right? Because on the ground. Okay, I'm not going up into the clouds. That would be vertical. Okay, but we still treat delta x and delta. We still treat delta x as that on a graph, the x-axis. The same with vertical projectile motion. If it's vertical, we're dealing with the y-axis of a graph. Alright, so you'll find with vertical projectile motion that we no longer use delta x, but we use delta y. That's the first thing worth mentioning. The second thing is that acceleration up until last year, grade 11, was also on a horizontal motion. We looked at acceleration of either a sprinter or an athlete, or a acceleration of a vehicle, or the acceleration of a box or a certain object. All right, we had to go and calculate that type of acceleration. Okay. However, with vertical projectile motion, we only know that there's one type of acceleration that exists, and that is the acceleration due to gravity. So wherever we see A in our equations of motion, we can replace it with the letter G. Okay, so a couple of things that change. All right, delta x becomes delta y, and acceleration doesn't have to, but can change to G, which is acceleration due to gravity. All right, it's not wrong if you write A in place of G, all right, in the equation of motion. It's okay, but if you write delta x in vertical projectile motion, your whole thing's wrong. It doesn't matter if your answer, your value is correct. But because it says delta x equals that, you will get it wrong. But if you calculate in a value for acceleration, which usually isn't even worth calculating, because I mean, if it's falling from the sky, well, there you go. It's gravity. No matter how heavy the object is, gravity stays the same. Doesn't matter. Okay. But if you use A instead of G, you don't get it wrong, because G is still acceleration due to gravity. It's still acceleration, still in meters per second squared. Okay. Now, There's a little bit of introduction. The Earth obviously pulls objects towards it. Okay, you and I, we are considered objects in the eyes of the Earth, if the Earth had eyes. Okay, because we are constantly being pulled down towards it. Alright, it's basically humbling us every day. Okay, that's why we don't fly. Okay, and it pulls us down with a downward gravitational force, okay, which is known as G, which is value is calculated at 9.8 meters per second squared. Right, we're familiar with that, okay? This is a force of attraction towards the center of the Earth and is known as the weight of the object, okay? It is constant downward. It is a constant downward force and leads to the constant or uniform downward acceleration of an object in the air, okay? Which is gravitational acceleration. So, it's a constant downward force no matter where I am in the sky. I drop anything, I will accelerate at 9.8 meters per second squared, no matter what. No matter what. Okay. A couple of important terms that I must make you all aware of, and by far the most asked term is free fall. I have seen free fall being asked countless times in the 5 years that I have been tutoring this subject, and I also saw it, I think, in one of my exams. I can't remember if it was in the final, it was in the June exam, or was in the mock exam. I can't remember my year. I mean, that was about like 8 years ago, so I'm kind of giving away my age, but I mean, who cares? I'm not sure, but it is by far the most asked. Okay, it's not always asked. Okay, sometimes it is stated the object is in free fall. Okay, so you may not be asked to give the answer, but you will be required to know and understand what free fall is. Alright, cool. Now, free fall, the term, is the unhindered movement of an object in the gravitational field. In other words, an object is accelerating due to one thing, and that is gravity. Number of ways we can state this as an answer. Free fall, an object is in free fall if the only force acting on it is the force of gravity. An object's also in free fall. In free fall, if the only force acting on it is the gravitational force, okay? Or free fall is the unhindered movement of an object in the gravitational field of the Earth. Unhindered meaning nothing else is causing this object to move but the gravitational force. I'm sure we can all grasp free fall. I'm sure we can, and I believe we can, but it's by far the most asked term. Okay? Another term that's also asked is the term projectile. Okay? I mean, we are dealing with vertical projectile motion. So the term projectile, this is an object that is moving through the air. Okay? An object may be experiencing free fall, doesn't have to, but may be experiencing free fall. Where was I? Yes, free fall after being dropped, thrown, or shot. Okay? So free fall free fall is not its entire journey, or it's not the start of its journey. If something is projected, it either had to be thrown, it either had to be dropped, or it had to be shot or flung. You know, shot doesn't need to be by a gun, but, you know, cannon, elastic band pulled and then released. That's a projectile. Object moving through the air, experiencing free fall after something was done to it. So either it was dropped, thrown, or shot. Okay? In the air resistance is small. If the air resistance is ignored, gravitational force is the only force acting on the projectile or on the object. So often in your question of vertical projectile motion, they will state that ignore the effects of air resistance, meaning it's so small, it's not even affecting our projectile or our object. It's the gravitational force is overcoming these the air resistance. Because believe it or not, they are air resistance. I mean, the air resistance can play a big role. Okay. But sometimes we can just ignore. Okay. So if you look at a couple of graphic representations of a projectile. Okay. So let's say here's a little bit of a cliff type thing, and here's the ground. Whatever, I drew it green because, you know, nature's cool. And object, okay, can either go from here all the way down here, okay, and that went obviously in that motion. Okay, an object can also go straight down. Okay, so it can either go straight down or it can go straight up. Okay, either way. Okay, straight up or straight down. An object can also go in this direction. Okay, so started here, thrown up, reached what we call here max height, H for height. Actually, let me just take that away. Max H, little h for height, and then came back down to its what we know as its starting point. Alright, obviously we know this motion here, thrown and going down a little bit of a curve, and then of course an object can go from here, thrown up all the way, and then landed over here. Okay, sometimes an object can even go from its starting point and land past its starting point. Okay, here's its starting point, but look where it landed. Can land past it. Okay, and obviously a good way of thinking about this is standing on top of a building. Okay, throw something up and you miss it, or you threw it a bit too far and it goes past the top of the building and goes down all the way down to the ground, the actual ground. Alright, that we see. Okay, so these are all just parts of motion. Okay, what we want to now that I've explained it, and I think everybody is a little bit more okay with me explaining that, is now looking at the equations of motion. I can't even spell the equations right. There you go. Okay, because we're obviously going to be using equations of motion a lot in our questions. Okay, so of course remember, for vertical motion we are doing vertical motion. It goes without saying, I don't even have to state that there. Okay, we're going with vertical motion. So we should remember the equation of motion. Vf is equal to Vi plus, now remember you can write G here or A. I'm going to write G delta T because it's vertical. I like putting G there for gravity so I don't get confused. Okay, and of course we've got Vf squared is equal to Vi squared plus 2G delta Y. I was going to make my Y a little bigger there. Let me just take that away. Delta Y. Y delta Y, vertical. Okay, not horizontal. Then we've got delta Y is equal to Vi delta T plus half G delta T all squared. And then our final one, we have delta Y is equal to Vi plus Vf divided by 2. Let me just draw my fraction in there. There we go. Brackets multiplied by delta T. Okay, so what can we see here with our equations of motion? That our equations of motions are not very much different, except that delta X becomes delta Y now, and A can become G, which is what I decided to write it as. Okay. Okay, graphs of motion. Okay, now graphs of motion for vertical projectile motion are different from the graphs that we are all used to from the equations of motion that we learned for horizontal. Okay, they are quite different. Okay, so they come also in different categories. Okay, so of course we're going to first have a look at the position time graphs. Okay, so I'm gonna do all of them and give a heading. So this is a vertical This is a graph for a vertical downward. Okay, downward projectile motion. Okay, there you go. Vertical projectile motion, that's downward. Okay? Other words, if I can draw it, if that's our object, it's going downward. Okay? So there's about 2 different graphs here that we can draw depending. Okay, so of course we got our position, which I just need to write on the side here. Position, remember we label the y-axis is position in meters. And of course we have time in seconds on the x-axis. Okay, but this is position time graph. Okay, put it back in this position. Let's start with the position before we get to velocity. So this is of a downward projectile motion. Okay, so if our upwards is positive, the graph will look like this. Okay, if upwards is positive. However, if you decided to take your downwards as positive, okay, the graphs can obviously look slightly different. Okay, I need to just make this line a little higher. Back over there. You still got time in seconds, and you still got your position time graph here. I just need to get you guys into the habit of labeling your graphs, because there's marks, labeling your graphs is marks. Okay, it's the same but just now inverted. So now that graph will go, it's very difficult to draw on a pen, but something like that. Okay, it's just the inverse of that, more or less. Alright, so upwards positive, obviously upwards is positive, we're in the top side of we're in the positive side of the graph. Okay, because this positive side of the graph, obviously that's the negative side. Okay, same like on a Cartesian plane, same thing. So our knowledge of the Cartesian plane must not be forsaken in our brains. Okay, we need to keep it. Alright, so it all depends on what you take as positive. Okay, if it was a downward, remember the object is going down. Remember this downward here? The object is already going down. Alright, so if you're taking the upwards as positive, this is how it will look. Okay, but if you are taking it the downwards as positive, then of course you would do that. Okay, just invert the graph. Okay, sweet. Okay, so we're going to keep this same thing, okay, and now we're just going to move on to the velocity time graph. Okay, now we're just going to have a look at the velocity time graphs for the same motion. Okay, of course now on the y-axis we're now no longer busy with position, we're now busy with velocity, which is now measured in what? Meters per second. Okay, so let's just add them in here. Writing to the side on a computer is quite a art, I think. You know, if you get it right, away. Cool. So for a upwards as positive for velocity, it's going to be in the negative direction, and I'm going to, in fact, I don't like white, so I'm going to just change the color so you can see the graph is going downwards. All right, like that. If you take upwards as positive, alright, then you are going, your velocity will be in the negative, because remember your velocity has a direction. Alright, so if the object is already going down and you take upwards as positive, then you cannot draw your velocity values in the positive side of the graph. However, if you take downwards as positive, so the object is going downwards and you're taking the downward motion as positive, then your velocity will of course go in the positive side or half of the graph. Okay, it'll look something like that. Okay, so it works differently to position. Okay. Something worth mentioning, and I'm going to write it over here, is that if you take the gradient, okay, if you take a gradient, okay, this is still of the velocity time graph. Let me just heading this. Velocity time graph. Okay, if you take the gradient, which is obviously equal to the change in velocity over the change in time, okay, of a velocity time graph. Now, what is this equal to? Change in v over change in t, you know, that is equal to acceleration. Okay, so your gradient would obviously equal to acceleration, which is equal to, in this case, 9.8 meters per second squared. Okay, if you took downwards as positive, and of course negative 9.8 meters per second squared if you took upwards as positive. Okay, because obviously you got a negative downward sloping, negative gradient, upward sloping, positive gradient. You get the point. Away. And if you take the delta y, if you want to find out the displacement of your object, all right, from a velocity time graph, all right, you simply just take the area under the graph. The area underneath a velocity time graph will equal the displacement. Okay, in that case of the what we just saw previously, yeah, we can see if we drop dotted lines here and here, we got triangles, right? So it'll be basically the area of a triangle, which will be equal to half base times by height. Okay, and then you'd get your answer, of course, in meters, right, for displacement. Okay, so that's how velocity time graph works. The gradient gets you acceleration, and the area underneath the graph will give you the displacement of the graph. Okay, and that's for the vertical downward motion. Okay. Right, so now what we're going to do is we're going to have a look at a projectile motion. Okay, but now the object is doing something different. We're going to look at projectile motion going up and down. Okay, and I'm going to have a look at it, and I'm going to write it in capital letters. When the object returns back to starting position. Okay, this is what we're going to have a look at. Okay, cool. So the position time graph for this one, we're going to have a look at the position. Okay, this one, pretty simple and standard. Okay, remember we still got time at the bottom here, which is measured in seconds. And then, of course, we got position, which is in meters. Okay, now, again, the first one, upwards as positive. It's a simple upward motion, reaches a peak and comes down. If upwards is the direction taken as positive, and of course, with a the opposite is also true. If it is downwards taken as positive, in other words, you take the downward motion part to be positive, then of course it's going to look the reverse of that, like that. Okay, obviously with both sides still labeled, position on the y and time in seconds on the x-axis. Okay, so if upwards is positive, of course up hits maximum height. We see the turning point is, that's maximum height where it stopped in the air and then started making its way down back to the starting point. So you see here, that line, this position here and this position over here is the starting point. So both it returned. So it returned to the starting point, which was also its end point. Okay, and that is the position. Okay, so the starting position was taken as the reference point, and that was obviously 0. Okay? Just having a look at the velocity time graphs for the same object. So in other words, it's going up and down and returning back to starting point. If you take your upwards as positive, and I'm going to use the red again, of course for the upwards as positive, if it obviously goes up and then it reaches a certain point in the sky and then starts making its way back down. Okay, so that's how it would look. I'm just going to use some dotted lines here quickly. Just draw it upwards here. Okay, there's my positive side and there's my negative side. And of course, if your downwards was considered positive, then of course it would start over here and then land up, of course, over here. And then I will use the dotted lines to draw over here. Okay, of course that's our positive side, that's my negative side. So to explain, if I choose upwards as positive, in other words, I threw my object up and then it came back down into my hand. So just throwing a tennis ball or a bouncy ball, or throwing your, if a person had a child, throwing a child up in the air, then catching her or him, doesn't matter. The velocity obviously starts as it goes up, starts at a certain point and then reaches its maximum height over here and then starts coming back down. Okay, starts coming back down. Remember, if the object was not slowing down, right, if the object was not slowing down as it was going up, of course it'll be Superman. Okay, but it slows down. The reason why it slows down is because of gravity. Gravity is pulling downwards at a certain acceleration. Goes up, hits it, and hits the maximum height, and then starts coming back down. Okay, if you use your downwards as positive, then of course this would be your upward motion. Okay, and this would be your downward motion. Over here, this would be your upward motion, and this would be your downward motion. Of course, if you take the gradient, it still gives you the same thing, which is 9.8 meters per second squared, the gradient of the velocity time graph. But delta y would be the area underneath the graph. So in other words, you got two triangles there in either graph, meaning that you'd have to take the sum of the triangles that's between the horizontal axis. So you got one triangle and then you add it to another one. So it's going to be half base times height plus half base times height, of course. If the triangles are the same size but in opposite direction, they will obviously cancel each other out. Right? So if they are the same size, in other words, there's the bases are the same. So from 0 to 5, and then from 5 to 10, of course, the base will be 5 each. And if it's the same height on either one, of course, they cancel each other out and they give you 0. So in other words, there's no acceleration. I mean, there's no displacement. Sorry, there's no displacement. Okay, so if you go 300 meters to the west, for example, if you just bring it back to horizontal motion, if we go 300 meters east and then another 300 meters back, we'll obviously end up back where we started because we're the same distance up and down. So displacement would be 0. Same thing. Right? Same analogy. We don't get rid of that analogy, of course. Okay. The next graph I'm going to show you, which is the final graph, then we'll see that this probably won't be the case, because our velocity time graphs will be different. Okay, so the next graph I want to show you is the graph of still of a projectile motion. Okay, but this projectile motion is also up and down. Okay, up and downward. Okay, the difference here is that this one is going past the starting point. Right, past the starting point or past the starting position. Okay, so let's have a look at position first, of course. Position time graph. Okay. Okay, now I'm going to do a slight bit of a cheat here. Okay. A slight bit of a cheat because I trust you all, and I'm going to forego, for time purposes, labeling my graphs, okay, or labeling my graphs in full. So I'm just going to use delta y here in meters. Delta y. Please don't label it like this. Please label position. And I'm just going to use delta t here. You can still use delta t in place of time in seconds. Delta t is still acceptable, but don't use delta y in meters, please. Don't do that. So past starting position, again the first one, if up is considered as positive and the second one is down is considered as positive. But if up is considered as positive, then the graph will go up and the graph will accelerate past the horizontal point. Of course, if it's going the opposite direction, just invert it. Okay? The starting point was taken as reference. So in other words, the starting point in both was 0. Okay, down was positive, the position that was going up first. Of course, this part here would describe, for the graph on the right, would describe the upward motion, and this positive part here would obviously describe the downward motion. Of course, if up was taken positive, then obviously this top half would be the positive motion. Obviously here, obviously up, turning point coming down, down, down. Here's the starting point, and then obviously the negative part there would be where it goes past the starting point, still in the downward position. Okay, so this would be the graph or position time graph of an object that accelerates past the starting point. Of course, we just need to take note and be aware of which direction we are taking to be our positive direction. Okay, and that's just for position. The velocity time graph for this type of motion looks just slightly different. Okay, in the previous example we saw more or less equal triangles. Okay, so in other words our displacement would equal 0 because the object was returning back to the starting point. So the same amount, the same distance it went up was the same distance that it was traveling down. Okay, but velocity time graph for, just fix my axes here, for a object that's traveling past a starting point, if the upwards is taken as positive, we'll start with a smaller triangle on top and go down to a bigger one at the bottom, as we can see here. Okay, reason being, this journey here after the horizontal, there's my positive, negative. So where you see the negative, this little journey here shows the velocity after it has gone past the starting point. And the opposite is also true for the downwards positive motion. We'll have a smaller triangle at the bottom with a bigger one on top in the positive half. Okay, so the positive half over here meaning the downward motion, because we're taking the downward direction as positive, and this little negative position here showing the upward motion. Okay, so here we've got positive on top, negative at the bottom, same thing here, same thing here. Okay, so the gradient will still give us the same answer for both of these. The gradient is gradient. Okay, and of course delta y would be the area underneath the graph, and we'll take the sum of those two graphs, which of course will get a actual value greater than 0 for our displacement. Okay, so that's the gist of it. Okay, so area underneath the velocity time graph gives us displacement, and of course the gradient would give us the acceleration. Okay, which in this case will always be 9,8, depending on which graph you take. If you take upwards at positive, 9,8. Sorry, upwards as positive will be negative 9,8, and downwards as positive would obviously be positive 9,8, because gravity is always going down. Alright, the acceleration time graph. The acceleration time graph, there is only 2. Okay, for the acceleration time graph. Okay, because an object can either be going up, if you take upwards as positive. Okay, so how this will work is you take it upwards as positive, of course you got time in seconds, and of course you got acceleration, which is, you could just use A, which is meters per second squared, but please write acceleration out in full. And of course can only be 9,8 or negative 9,8 in this case, If you take upwards as positive, your acceleration value will be negative. Okay, showing that obviously upwards is your positive, so everything downward is negative. Of course, if your downward is positive, of course, then your acceleration is going to be positive 9,8. Okay, and it will look like that. It will be in the positive side of the graph. Okay, that's how it look for up and downward as positive, and that's why I said acceleration is by far the easiest graph to ever draw. Okay, in this case. The example, question 1, a boy stands on the edge of a cliff. He throws a stone vertically upwards with an initial velocity of 12 meters per second. The stone strikes the ground below the cliff after 4 seconds. Ignore the effects of air resistance. So there you see, ignore air resistance. That means we ignore it, and often that will be stated in the question. Alright? So we can definitely picture this motion. He stands on a cliff, throws something upwards, and the stone strikes the ground below him. So after we've just gone through graphs now, we should already know the graph for this type of motion if we are required to draw it. If we are, but I doubt we will be. Question 1, what is the magnitude and direction of the acceleration of the stone when it's moving upward, when it reaches maximum height, and when it is falling down? Alright, 2 marks each. I guarantee you they'll all have the same answer. That's just a hint. Okay, 1.2, at what time does the stone have a speed of 3 meters per second? So that, of course, is an equation of motion. And 1.3, also, how long does it take the stone to reach its maximum height? Well, of course, that's also an equation of motion. And 1.4, determine the height of the cliff. So not the maximum height of the that the stone reaches, but the height of the cliff that the boy is standing on. Alright, so let's give this a crack and we'll mark it in a few minutes. So just to answer question 1 first, of course, we start 1. Besides all the information that we still see given on the screen, they ask what magnitude and direction, or what is the magnitude and direction of the acceleration of the stone when it's moving upwards. Now, they're asking for the magnitude, which is obviously the value, the size, the numerical value, and the direction of what? Not the motion, but the acceleration, alright, of the stone. Alright, so if I come just to my little answer, little layer here, so I've got question 1.1, 1.1.1. The question was, there's it, when it's moving upwards. Well, my answer to that is simple. The acceleration due to gravity is always going down. So the magnitude and direction of acceleration when the stone is moving up is still 9,8 meters per second squared. That looks like an 8. Let me just change that. Meters per second squared downwards. It doesn't matter on the motion. The motion, though, the stone is going up, yes, but gravity is still a downward force, a downward acceleration. The gravitational force is still going down. 1.1.2, when it reaches its maximum height, same answer, 9,8 meters per second squared. Write that a little bit there, squared, still downwards. Doesn't change. 1.1.3, when it is falling down, obviously now it makes even more sense. 9,8 meters per second squared downwards. Always. Gravity is always going down. Right? That should have been your answers for 1.1 all the way through to 1.3. 9,8 meters per second squared downwards. Alright, so I'm just going to do the solution now for 1.2. At what time or times does the stone have a speed of 3 meters per second? Now remember, the boy stands on a cliff, throws the stone upwards, and then obviously the stone falls down. Okay? So for 1.2 we're going to have the first motion is the upward motion. So if my upward motion I've chosen as positive, okay, then the solution is going to go as follows. I use the equation of motion, hopefully we all chose this one. Vf is equal to Vi plus G, if we used A it's fine, delta T. Now Vf, they want to know obviously when it was 3. So positive 3 upwards. And here I've got 12 was my initial velocity. Also, it was thrown 12 meters per second upwards, plus negative 9,8 delta T. Why is it negative 9 delta 8? Because the stone was going upwards first. Okay, so here I'll have positive 15. Okay, I'll have positive 15 over here. And let's see, negative 9,8 delta T. I divide both sides by negative 9,8. Delta T would obviously have calculator. Where's my calculator? There it is. Okay, cool. 15 divided by negative 9,8 would give me 1.53 seconds. 1.53 seconds. 1.53 seconds, and that would obviously be upwards. Yes, what's up? Let's discuss this.
Isn't it the 12 going over, it becomes negative 12?
Yes, of course. Sorry, boys.
It's a 9.
Sorry, thank you for that. That comes
Then
negative
it
12,
becomes
so it
0.2.
So 3 minus 12 should be negative 9, right?
Yes.
Yes, of course. And then it becomes, so then that should ends up does being a positive number. I was actually questioning myself there, like something was wrong, but couldn't figure it out. So 9 divided by 9,8, and that becomes 0,92. Yes, as you said, 0.92 seconds. That's when up is positive. So that's when it's moving upwards at 3 meters per second. But now, of course, it changes direction, obviously coming down. So obviously, it will come down and it will obviously accelerate to 3 meters per second. We still use the same formula. Vi plus A delta T. I'm only writing A just in case anybody wrote A in their answer. It doesn't matter, it's still right. So still 3 as for your Vf. Okay, remember it's going down, so this becomes negative 12. Okay, plus 9,8 delta T. And that goes over, that of course becomes 15. 3 plus 12, of course. And then that's equals to 9,8 delta T. Divide both sides, and therefore delta T is equal to, this is 1,53. So let me just write that 1 properly. 1,53 seconds, of course, and that's correct. Okay, sorry about that little boo-boo earlier. That was my bad. Okay, so first when it moves upwards, it gets to 3 at about like 0,92 seconds, and then move downwards, it gets to 3 at about 1.53 seconds for 1.2. For 1.3, the question was, how long does the stone take to reach its maximum height? Okay, so for this we use the same formula. Vf is equal to Vi plus G delta T. Maximum height is obviously when it's up as positive. So once it reaches maximum height, all right, what do we know? Vi is equal to 12 meters per second. Maximum height is obviously going upwards, so I'm choosing upwards as my positive direction. Okay, my Vf, remember, once it reaches maximum height, it stops for a few seconds. It stops briefly, maybe for a second or two, or just over a second, but under 2 seconds, or maybe even a few milliseconds. But it stops briefly. Okay, so I know once it stops in the air, if anything comes to a stop, the velocity will be 0. Okay, and I do know that that was going upwards, so hence value for G is going to be negative 9,8 meters per second squared, because gravity is always going down. Okay, so we sub in our values. 0 is equal to, this is positive 12 plus negative 9,8 delta t. So you swap it over, I've got negative 12 is equal to negative 9,8 delta t, and divide both sides by negative 9,8, and I do get my delta t to equal 1,22 seconds, meaning that after 1,22 seconds my stone reached its maximum height before turning around and coming back down to past starting point to the ground. 2 marks. For some reason that was 2 marks, and we did more than 2 marks worth of work though, but 2 marks. 1.4, determine the height of the cliff, for 3 marks. Okay, so 1.4 might have been a bit of a difficult question to attempt first, okay, but it's the same. We obviously need to use an equation of motion that has delta y in it. Okay, so equation of motion that's very good to choose is delta y is equal to vi delta t plus half a delta t squared. Remember I said a or g, doesn't really matter. I must reiterate this so we understand. Okay, so coming back to the question, it says here initial velocity was 12 meters per second and the stone strikes the ground below the cliff after 4 seconds. Okay, so remember the question we are trying to find out was determine the height of the cliff. So the stone reaches a maximum of a delta y of 0 after 4 seconds. We're trying to obviously determine the height of the cliff. So after 4 seconds, displacement for the stone is equal to 0 because it hits the ground. Okay, so it must have fallen obviously from a certain height, and we need to find out that value. So my delta y is still unknown. My initial was obviously 12, and you can see which motion I'm taking as positive, upwards. And delta t is going to be 4 seconds, because 4 seconds it struck the ground, plus half, of course, and now I add in my negative 9,8 because gravity is always going down, but my stone went up first, and 4 seconds squared. You know, you don't get negative time. Okay? So here you got 48, and that's going to end up being negative because of that negative. So I just want to make sure half of negative 9,8, that's probably negative 4,9, times 4 squared, that's minus 78,4. Minus 78,4. And then, therefore, my delta y is going to equal negative 30,4, which is basically equal to 30,4 meters. And therefore, the height of the cliff is 30,4 meters. And the reason we got a negative, because obviously the stone fell downwards. So that's why we got a negative. Okay? Picture the negative part of the graph. The stone went up and then went down. So the height of the cliff was 30,4 meters. Okay? And we state that is the height of the cliff. Okay. And that concludes my presentation for this week, grade 12. Please stay tuned for next week, where we will continue practicing some examples in vertical projectile motion.